Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. The cosmic microwave background. A faint whisper across the eons. The cosmic microwave background. Imagine a faint whisper echoing through the vast emptiness of space. This isn't a sound wave, but a message encoded in the form of ancient light. The cosmic microwave background radiation, CMB. This relic radiation, bathing the cosmos in a faint microwave afterglow, is a direct echo from the very dawn of our universe. It's not a sound we can hear, but a signal picked up by sophisticated instruments, offering a glimpse into a time roughly 380,000 years after the Big Bang. The universe back then was a very different place. Forget the galaxies, stars, and planets we see today. Instead, picture a hot, dense soup of elementary particles and pure energy. This primordial state was opaque, meaning light couldn't travel freely. It was like peering through a thick fog. You might sense there's something beyond, but you can't quite see it. The CMB is the faint afterglow of that very early universe. During a pivotal moment called recombination, around 380,000 years after the Big Bang, something remarkable happened. As the universe expanded and cooled dramatically, it transitioned from an opaque to a transparent state. Electrons, previously bouncing around freely, were finally captured by protons and neutrons, forming the first neutral atoms, primarily hydrogen. This seemingly simple act had a profound consequence. Unlike charged particles, neutral atoms don't scatter light as efficiently. With the fog of charged particles clearing, the universe became transparent, allowing light to travel freely for the first time. The CMB is the echo of light emitted during this recombination epoch. These photons, initially bathed in the intense heat of the early universe, have been traveling for billions of years. As the universe expanded, these photons stretched and cooled, losing their energy and shifting from the visible and infrared spectrum to the microwave range. This faint microwave afterglow is what we detect today, a faint whisper carrying information about the universe's state in its very infancy. The Big Bang, beyond the explosion. The term Big Bang often conjures images of a giant explosion happening in space. However, the Big Bang wasn't an explosion in the traditional sense. There was no central point from which everything erupted. Instead, imagine a balloon. As you inflate the balloon, the surface, representing space-time itself, expands rapidly in all directions. This is a more accurate picture of what happened during the Big Bang. In the first fraction of a second after this rapid expansion began, the universe went through a period of incredibly rapid inflation. This wasn't just a simple expansion, It was an exponential growth of space-time itself. Imagine the size of the balloon doubling, then doubling again in a blink of an eye, and continuing to double at an even faster rate. This period of inflation is crucial to our understanding of the universe's structure and evolution. It explains the vastness of the observable universe and the remarkable uniformity of the CMB radiation. The birth of particles and forces, from primordial soup to building blocks. The universe that emerged from the Big Bang was vastly different from the one we inhabit today. It was a hot, dense soup of elementary particles, fundamental building blocks of matter and energy, existing in a state unlike anything we can recreate in laboratories. Here, the four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, weren't distinct entities. They were unified into a single, primordial force. As the universe expanded and cooled rapidly, this unified force began to break apart. Imagine a single, complex molecule splitting into its constituent atoms. Similarly, the primordial force separated into the four distinct fundamental forces that govern our universe today. Each force took on its own unique set of properties, dictating how particles interact with each other. This separation also triggered the formation of the first subatomic particles, quarks. These tiny particles, the building blocks of protons and neutrons, emerged from the primordial soup. Quarks didn't exist freely for long. As the universe continued to cool, these quarks combined to form protons and neutrons, the fundamental building blocks of atomic nuclei. The first atomic nuclei formed in the early universe were primarily hydrogen and helium, the simplest and most abundant elements. The universe was still far from the star-filled cosmos we see today, but the seeds for its future complexity were sown. With the emergence of distinct forces and the formation of the first atomic nuclei, the stage was set for the next crucial chapter in the universe's story, the epic of recombination and the faint echo it left behind in the form of the cosmic microwave background radiation. Recombination, a turning point in the cosmic story. Imagine a thick fog slowly clearing, revealing the world beyond for the first time. This analogy aptly describes the pivotal epoch of recombination, roughly 380,000 years after the Big Bang. The universe, previously a hot, dense soup of charged particles, began to cool dramatically due to its rapid expansion. This cooling had a profound effect on the behavior of light. Before recombination, the universe was filled with free electrons. These energetic electrons constantly interacted with photons, the fundamental particles of light, scattering them in all directions. This scattering acted like a thick fog, preventing light from traveling freely. The early universe was essentially opaque, shrouded in a sea of charged particles. However, as the universe cooled, a critical threshold was reached. the energy of the photons, remnants of the Big Bang's intense heat, became sufficient to overcome the binding force holding electrons to atomic nuclei, primarily protons. This process, known as ionization, ripped electrons free, allowing them to roam the universe independently. However, the universe's continued cooling had another consequence. The freed electrons no longer had enough energy to remain unbound. They were eventually captured by protons and neutrons, forming the first neutral atoms, primarily hydrogen. This seemingly simple act of electron capture, the transition from a universe dominated by charged particles to one filled with neutral atoms, marked a turning point in cosmic history. Neutral atoms, unlike their charged counterparts, don't scatter light as efficiently. With the fog of charged particles clearing, the universe underwent a dramatic shift from opacity to transparency. Light emitted during this era, roughly 380,000 years after the Big Bang, could finally travel freely through space, unimpeded by interactions with charged particles. A fossil light preserving the universe's infancy. The faint microwave radiation we detect today as the cosmic microwave background radiation, CMB, is a remarkable echo of the light emitted during recombination. These photons, bathed in the intense heat of the early universe, have been on a remarkable journey for billions of years. As the universe expanded, these photons stretched and cooled, losing energy and shifting their wavelength from the visible and infrared spectrum to the microwave range. This dramatic shift, known as redshifting, is a consequence of the universe's expansion. Imagine stretching a spring with a red ball attached. As the spring stretches, the distance between the coils increases, effectively stretching the wavelength of the light waves interacting with the ball. Similarly, as the universe expands, the wavelength of light traveling through it stretches, shifting its color towards the red end of the spectrum. The CMB radiation we detect today, faint and in the microwave range, is a testament to this redshifting process. The CMB is more than just a faint afterglow. It's a fossil light preserving a snapshot of the universe at a very young age. By meticulously studying the CMB's temperature fluctuations and polarization, a special property of light, scientists can glean crucial information about the universe's conditions during recombination. These tiny variations in temperature and polarization act like fingerprints, hinting at the subtle differences in density that existed in the early universe. Denser regions, with slightly more matter, had a stronger gravitational pull, attracting more matter over time and eventually forming the seeds for the large-scale structures we see today. Galaxies and clusters of galaxies. The CMB is a treasure trove of information, offering a window into the universe's composition, its age, and even its overall shape. Unveiling the CMB's secrets, a journey of discovery. For decades, the CMB remained a theoretical concept, a prediction of the Big Bang Theory. However, In the early 1960s, two American radio astronomers, Arno Penzias and Robert Wilson, stumbled upon a faint, persistent noise while calibrating their antenna for satellite communication. This unexplained noise, uniform across the sky and consistent throughout the year, defied explanation. It wasn't a signal from any local source, but rather a faint echo from the distant past. The discovery of the CMB by Penzias and Wilson was a landmark moment in cosmology. It provided the first concrete evidence for the Big Bang theory. The remarkable uniformity of the CMB across the sky supported the idea of a homogeneous and isotropic, uniform in all directions, early universe. However, upon closer examination, scientists discovered a crucial detail. The CMB wasn't entirely uniform. It exhibited tiny fluctuations in temperature, on the order of 1 part in 100,000. These temperature variations, although minute, held immense significance. These subtle temperature fluctuations in the CMB were the first clues to the universe's slightly uneven distribution of matter during recombination. Denser regions, with a higher concentration of matter, were slightly hotter, while less dense regions were cooler. The imprints of inflation, a theory takes shape. The remarkable uniformity of the CMB, coupled with the observed large-scale structure of the universe, galaxies and clusters of galaxies, presented a fundamental challenge to cosmologists. The problem stemmed from the limitations imposed by the speed of light. In the time since the Big Bang, light could only travel a finite distance. This implies that regions of the universe now separated by vast distances could never have been in thermal equilibrium, meaning they couldn't have shared the same temperature. Yet, the CMB's uniformity suggested a surprising level of homogeneity across the cosmos. This apparent contradiction led to the development of the theory of cosmic inflation. Proposed in the late 1970s, inflation posits a period of extremely rapid expansion in the universe's very early moments, just fractions of a second after the Big Bang. During this inflationary epoch, the universe is thought to have undergone an exponential growth spurt, expanding by a factor of trillions or even more. This rapid expansion could explain the observed uniformity of the CMB. Imagine inflating a balloon rapidly. Initially, there might be small, localized variations on the surface of the balloon. However, as the balloon expands exponentially, these variations become stretched out and smoothed over, leading to a more uniform surface. Similarly, inflation proposes that the early universe's slight irregularities were stretched to vast scales during the inflationary epoch, resulting in the remarkable uniformity observed in the CMB. The theory of inflation also offers an explanation for another cosmological puzzle: the horizon problem. Light can only travel at a finite speed, limiting the observable universe to a specific horizon. Yet, the CMB's uniformity suggests a much larger region was in thermal equilibrium. Inflation proposes that the universe was much smaller before inflation, allowing distant regions to interact and reach thermal equilibrium before inflation rapidly stretched them apart, creating the vast, seemingly uniform universe we observe today. Unveiling the secrets of polarization beyond temperature fluctuations. The CMB offers more than just temperature variations for cosmologists to analyze. Light can also exhibit a special property known as polarization. Imagine a light wave vibrating in all directions like a skipping rope. In polarized light, these vibrations are restricted to a single plane, like a skipping rope held taut and moving only up and down. The study of CMB polarization is crucial for further refining our understanding of the early universe. Different physical processes can leave distinct imprints on the CMB's polarization patterns. These patterns can be categorized into two main types: E modes and B modes. E modes are primarily generated by the scattering of photons from density fluctuations during recombination. They provide additional information about the universe's early structure and evolution. However, the B modes hold a special significance. These patterns are predicted to be a faint signature of gravitational waves, ripples in spacetime itself, generated during the inflationary epoch. Detecting these B modes would be a major breakthrough, offering direct evidence for inflation and providing clues about the nature of inflation itself. The challenge lies in the fact that B modes are much weaker than E modes. Scientists are constantly developing ever more sophisticated instruments to detect these faint B mode patterns in the CMB. Such a detection would be a pivotal moment in cosmology, solidifying our understanding of the universe's early inflationary period. A treasure trove of information. Unveiling the universe's secrets, the CMB is akin to a cosmic Rosetta Stone, offering a wealth of information about the universe's composition, age, and overall geometry. By meticulously analyzing the CMB's temperature fluctuations and polarization patterns, scientists can infer a vast array of crucial parameters. One key insight gleaned from the CMB is the universe's age. Precise measurements of the CMB's temperature fluctuations allow scientists to estimate the time elapsed since the Big Bang. Current data suggests the universe is roughly 13.8 billion years old. The CMB also provides clues about the universe's composition. The relative heights of peaks in the CMB's power spectrum, a plot showing the strength of temperature fluctuations at different scales, reveal the proportions of ordinary matter, dark matter, and dark energy. Ordinary matter, like the atoms that make up stars and planets, constitutes only a small fraction of the universe's total mass-energy content. The vast majority is made up of mysterious dark matter and dark energy, whose exact nature remains unknown. Furthermore, the CMB offers insights into the universe's overall shape. The geometry of the universe, whether flat, open, or closed, can be inferred from the CMB's fluctuations. Observations suggest the universe is very close to flat, which aligns with the predictions of inflationary theory. The CMB also holds clues about the reionization epoch, a period roughly hundreds of millions of years after the Big Bang when the first stars and galaxies formed. A beacon for the future. Pushing the boundaries of knowledge, the CMB remains a powerful tool for cosmologists, offering a window into the universe's earliest moments. New space missions and ground-based experiments are constantly being developed to push the boundaries of our knowledge. These missions aim to map the CMB with even greater precision and sensitivity, unlocking further secrets about the cosmos. One such endeavor is the Simons Observatory, a next-generation observatory specifically designed to study the CMB. Equipped with highly sensitive detectors, the Simons Observatory aims to capture the CMB's faint B-mode polarization patterns with unprecedented accuracy. Detecting these B-modes would be a landmark achievement, providing concrete evidence for the theory of inflation and offering insights into the nature of inflation itself. Another ambitious project is the proposed CMB Stage 4, CMB-S4, experiment. This large-scale collaboration aims to create a network of telescopes strategically placed around the globe to observe the CMB with unparalleled sensitivity. By combining data from these telescopes, CMB-S4 hopes to achieve a much higher resolution image of the CMB, revealing even finer details about the early universe's structure and evolution. The quest to understand the CMB continues. These next-generation missions and experiments hold the potential to revolutionize our understanding of the universe's origin and evolution. By studying the faint echo of the Big Bang, we may uncover the nature of dark matter and dark energy, the dominant components of our universe. The CMB might even reveal clues about the existence of primordial gravitational waves, ripples in space-time generated during a theorized period of inflation. The exploration of the CMB is a reminder that by studying a faint echo from the distant past, we can unlock the secrets of our cosmic origins and chart a course for future discoveries. The faint afterglow of the CMB continues to illuminate our understanding of the universe, a beacon guiding us towards a deeper comprehension of the cosmos. As we delve deeper into this cosmic echo, we embark on a journey to understand not just where we came from, but also the ultimate fate of our universe.